What's going on, everybody? Good morning. Apologize for the few-minute delay, but I actually left my coffee downstairs, so I had to go get my coffee. All right, so who's checking in? I want to see if everything looks good and sounds good before we get rolling. As always, I'll get started with the schedule. Kind of give you a moment to say hello and check in and let me know if you guys can hear me okay and if everything looks good. So, what's going on, Connor and Kaylin, my two regulars? All right, looks like it's okay. Okay, so today we will do one or two questions regarding specific heat and converting units and what have you. Maybe apply it to the bomb calorimeter. To be honest with you, if you can do the harder questions for the specific heat, you should be able to handle the bomb calorimeter question or the two or three that we did yesterday. It's just a conceptual thing. All right, so schedule. A couple questions today. I'll post up an assignment in a little while today. It'll be due Monday at noon. We will have Monday's class to figure out any last-minute questions, do a Q&A, and then I will post up an assignment. It'll be the last assignment for this unit, and I'll give you a couple days on it. All right, so let's say get an assignment today, due noon. That same day, Monday, you'll get another assignment. It'll be the entire unit worth of stuff. Now, I understand this unit's a bit rough, okay? And traditionally, that's just what happens with this chapter. So I tend to take my time towards the end of it, and I think we've been dragging it out. So you'll get you'll get a couple days. So if I post it up on Monday, the final assignment for this chapter, it'll probably be due Wednesday or Thursday, something like that. And that'll give you multiple days, video opportunities to ask questions. And as far as I know, all grades are going to be a quiz. Everything except for the last assignment of the unit is going to be graded on if you completed it. But the last assignment of the units are going to be graded on accuracy and if you got the question right and this and that. All right, so the assignment earlier this week and the one coming up today, just do it, right? You'll get a grade. The one that will be given out on Monday will be graded for accuracy. So another reason why I want to give you guys some time to get that figured out. So, Connor, I hope that answered your question. It's going to be a quiz. Everything's a quiz, but this one's going to be graded on accuracy. Hope that makes sense. Okay. Before we get rolling, you guys have any specific questions? Anything at all? I'm all ears. I'm willing to talk about almost anything. All right, so Connor, you seem all right. Okay. Let's do green today. All right, let's go to the whiteboard, okay? Now, the whiteboard, I've been playing with it, and I think the settings are cool, all right? I got my area that I can write in mapped out. That's what the blue lines are all about. So I still got to play with the autofocus, I guess. But anyway, all right, so let's make up a question. All right, let's do a bomb calorimeter question, and then we'll do, I'm making these up, all right? You know, it is what it is. All right, so you got your bomb calorimeter, all right? I don't have any of the pictures ready, but you can go back and watch the other videos about those pictures, or just Google it, bomb calorimeter diagram. Something like that will pop up, no problem. Okay, let's say, I'm really dragging this morning. So let's say we got a question. Drawing a blank here. All right, let's say we want to solve for calculate joules per gram of a substance in a bomb calorimeter. Okay? So that's what we need to do. So we need to solve for that info. And in doing so, we're going to have to get some information, okay? Let's say there is 3.5 liters of water 3 points increased in temperature by, I don't know, 4.3 degrees Celsius after, let's do 1.8 grams of the substance. Whoa. I don't know what that letter was supposed to be. Was ignited. All right, so I'm making sure we got everything we need before we proceed. So we're looking for joules per gram of the substance. And we started with 3.5 liters of water. The temperature of the water went up by 4.3 degrees after 1.8 grams of the substance was ignited. Okay, this seems like a reasonable thing. We can do this. All right. I don't like the green. Actually, that looks pretty good. I'll take it. I'll leave it. Please pardon my dirty hands. It's just the way of life for me. Okay, so what you got to realize is that there is a Q that's being transferred from one thing to another, right? Remember the lead pellet question and then the glass and water question? So if we could figure out the Q of one thing, the other thing, the other substance would have an equal but opposite Q. So let's look at it from that perspective, okay? So in this case, we should be able to find the Q of water. We should have an M, we should have a C, and a delta T. Well, we don't have an M, but we do have a V. And the V of water is easily converted. So let's do that first. 3.5 liters. This is of water. Let's get rid of the liters, go to milliliters. Get rid of milliliters, go to grams. Now, this is just the density of water, no big deal. So you're going to multiply that by 1,000. So I get 3,500 with 2 sig figs grams. Now, that's my mass of the water. I can just plug it into this formula here. Okay. The C, you should just know off the top of your head. That's one of those numbers that you got to be aware of, kind of like the density of water. You just got to know it. The C of water is 4.8 joules per gram degrees Celsius. The delta T looks like it went up by 4.3 degrees. In a bomb calorimeter, the delta T for the water will always be positive. It's just how these things work. All right, now let's go to my calculator. I swear I'm gonna order one through Amazon. I'll get some fancy scientific calculator, something or other. All right, now with the numbers that we got here, it looks like we need 2 sig figs. So the value I got with 2 sig figs is 63,000. And that's going to be in joules. 1, because it's Q. 2, the units cancel out. Now, that's only part of the answer. That's only part of the procedure, okay? So we know that we need to keep going and calculate the joules per gram. So we know the total number of joules, right? Well, we want joules per gram. And we have, 1.8 grams? So that's the last part. So with sig figs, 63,000 divided by 1.8, and I get, wow, how did I do that? Exactly 35,000. Now the question could continue. I don't want you to think that this is it. It could continue and really say, calculate the kilojoules, right? Say I changed the question way up here, and it was kilojoules instead. Well, all you got to do now is the last step would be to convert this into kilojoules, okay? And then you would get 35 kilojoules per gram. Now, this seems like a more reasonable number to use. Your numbers would change based on the units. So in this question that we made up, we hit upon bomb calorimeters, specific heat, and converting units. We did that a couple times. So this is a good catch-all question. Not that complicated of a question, but we can do the like the lead pellet question. Let's do that one next, Okay, I'll see if I can bring up a copy of it. I won't be able to show you guys because I don't have this prepared, but I can at least bring it up on my screen here, and I can kind of read it to you. All right. So whether it be, let's see. Yeah, I can. Once I get it up here, I'll just tell you what the question is. In the meantime, let's use this opportunity, since I'm taking forever, to ask any questions in the chat, or clarify anything that you might have. So we got Kaylin and Connor. Kaylin, you good? Is this all making sense? Haven't heard from you yet. All right, so let's see. Looking for the lead pellet question. I'm pulling up like an old quiz that I would have used, and I can easily find any question I need here. Okay, so this would have been the question on the quiz. All right. All right, Kaylin, you're good. Cool. All right, so let's put my cap back on here. We're going to be doing the lead pellet question. Now, there's a really good chance I already did this exact set of numbers with you, but it's not that bad. Okay, once you do this a couple times, you're going to be fine. So I got my question up here. I'm going to apply it to the whiteboard and see what we can do. Now, the worst part is you guys just can't see the question. That's, kind of a drag. So I'll read it to you, and we'll start breaking it down. All right, so it says lead pellets, 0.09 kilograms. So I'm just going to write that down. Lead pellets, like little BBs. We got 0.090, so 2 sig figs, kilograms. They were heated to 100.5 degrees Celsius. So the initial temperature of the lead, all right? So T initial, TI, you'll see it in a moment, is equal to 100.5 degrees, okay? Then it was placed into 110 milliliters of water. So the water, since it's in milliliters, we can just switch it to grams. We got 110.0 grams, so 4 sig figs. The initial temp of the water was recorded at 24 and went up to 28. So the delta T of water, we already got that part figured out. That's going to be plus 4 degrees. Let's see. The experimental value. What is the experimental value of C of lead? So that's what we're ultimately trying to calculate. Again, you'll see the whiteboard in a moment. Let's just do that now. Okay, this is what I got written so far. And then this is the first thing we're doing, and then we want to do the percent error. If the actual value is 0.11. So let me put that up here. Actual value is 0.11 joules per gram degree Celsius. All right. So that's everything that the question's giving us, but it's not everything we know. So what I need to do, we know we got to solve for C of lead, and we got to get the percent error. So I'm going to erase this just to give me some room, and we're going to start building that chart, okay? Now, can you see the board now? I think I switched it over, okay? Let's see what it might... Yeah, okay, so you should be able to see the board now. Okay, let's make our chart. So we know we got a Q, an M, a C, and a delta T, and we're going to have two substances. One's lead, one's water. All right? Build this little chart here. Let's fill in what we got. Now, the lead is going to have a mass in kilograms. We want it in grams, so we're going to multiply that by 1,000. So this comes out to be 900, but with 2 sig figs. So 900 grams. Let's make that a little bit more like a 0. All right. Then for the water, we know we have 110 grams. Then delta T of the water, we got 4 degrees Celsius. Now, we also know that we have for the lead, or for the water, a C. We know it's going to be in joules. We know it's 4.18. Now, for the delta T of the lead, we have TI, or T initial. Okay, that's what the temperature started at. And then we know it went to 28 degrees. It went down to 28 because that's what the water went up to. So delta T of the lead is going to be the first thing we calculate. We got 100.5 minus 28. We get 0.5. Make that a 9, so 1. Make that a 9. That's 71. It's going to be 72 degrees with sig figs. So negative 72. I think you get what I'm trying to do here. Really struggling because I'm writing like this whatever. I don't care. Okay. This is what we're trying to get to. We're trying to get the C of the lead. Then we can calculate the percent error. So let's solve for Q of the water. It's the only thing on this chart that we can get to immediately. And then we know we're going to have an equal but opposite. We also know based on the delta T that this is going to be a positive and this is going to be a negative based on the delta T's again. So Q equals MC delta T. All right, so M for water, C for water is 4.18 joules, gram, degrees Celsius. Okay, and then delta T is going to be 4. All right, let's take a look at this. So we got 110 times 4.18 times 4. So if we're just guessing, this is around 440. So we're talking around 1,600, 1,700 maybe. 110 times 4.18 times 4. Okay, that was a little off. With 1 sig fig, it's going to be 2,000. Mine would have rounded to 2,000 anyway. I probably should have mentioned that. So this is going to be joules. Grams cancel out, degrees cancel out. So let's add that here. Let's go back to this chat thing here. I'm keep switching windows and it's a mess. All right, now we know that we have a negative 2,000 joules here for the lead. Okay. Next thing we could do is solve for C of the lead. Notice my little notations there. All right, so we should have a Q, we should have an M, we should have a delta T. The Q comes out to be negative 2,000. M, 900 with 2 sig figs. Multiply that by your negative delta T. Make sure you put the... Sorry about the noise if you're hearing anything. I got my windows open. Make sure you put the denominator in parentheses, so when you do that, your order of operations stay consistent. And then we're going to do the division here. So immediately after this, I'm going to go and order a calculator. I swear, I know I say that every day. Oh, man. I'm trying to do this with one hand. Okay. I got something that needs 1 sig fig, so I got 0.03. Hopefully you guys got something similar. And, yeah. Okay, so that would go in that chart, and that's the first part of your answer. The last part is just doing the percent error. Now, percent error, if you remember how to do that, it's going to be the difference between what you got and what you should have got, right? That's your error. So do the absolute value, 0.03 minus 0.11. Divide that by 0.11 times 100. And then you get your answer. Now, sig figs are going to play a very important role here. So 0.03 minus 0.11. And I get 0.08. And then you got to divide that. So 0.08 divided by 0.11 times 100 with 1 sig fig. So I got 70%. 70%. I hope that makes sense. And if you guys were following along there, it's not a bad question anymore, okay? I remember the first couple times we tried that, there was normally in class, like this is a jaw-dropping question, the first time you guys see it, and it's like, what are we doing? Well, I think the two of you that keep coming back to class, you know, see? Kaylin, you're saying it makes sense already. Very good. So I'm totally confident that you guys will be just fine, okay? So let's do one more assignment as practice. I'll put that up shortly. Do Monday. Then Monday's assignment will get posted when I get to making it, because I got to make the whole thing from scratch. Whatever. All right, so assignment today, general practice, bomb calorimeters, Q equals MC delta T stuff, right? That will be due on Monday. Then they'll have another assignment that goes all the way back to the very beginning of the unit, and that one will count for accuracy. Take a couple days, get that figured out, ask me some questions along the way, and we can get you rolling, get you a good grade, and then we'll figure out what to do with the rest of the year, okay? What we will probably do is stuff that I want to talk about because there's plenty of stuff in chemistry that we just don't have time normally to even scratch the surface of or discuss. So we might be doing some other things, because after this unit's over, we then have satisfied the curriculum as best as we can. All right? So maybe there's a couple things we could do. We could do like a movie assignment where you watch a movie, answer a couple questions. That you could do. I'll give you several days for something like that. We'll work it out. Whether it's something like that or it's other topics that you guys didn't see because we didn't do the honors curriculum with you, that's an option as well. But it will not be like super heavy duty. I promise it won't be, mentally taxing. It'll be more of, we still have time and we have the obligation to continue learning. So we'll look at it in that regard. I hope that makes sense. All right, so I'm going to back out of this and start preparing an assignment. It'll probably be up this afternoon, okay? No later than tomorrow morning, all right? Just because of everything that's going on in my life at the moment, all right? Are we good? Is everybody okay? Give me one way or another that everything is copacetic and you guys are good and you understand the timeline with the schedule and what these assignments are going to be worth and all that stuff. So I need to hear from both of you guys before I move on. So give me a thumbs up, or you can ask a question. All right, so Connor's good, just waiting on Kaylin. Hopefully she didn't take off in the last 2 or 3 minutes. And once we hear from her, I will put my little thumbnail back up and move on. All right, guys, cool. That's it. Have a good weekend. Get that assignment taken care of. And don't look for it right away. All right, I'll get that up probably after my honors class at 9. So maybe by noon I'll have it up. All right, cool. I'll talk to you guys on Monday. 8 a.m. at the moment is the schedule, and I'm pretty sure the weather next week is going to cooperate. We'll see. All right, cool. I'll talk to you guys on Monday. See ya. All right, what's going on, everybody? Today we're just going to do a couple questions, learn some vocab, and go from there. So while I give everybody a chance to kind of check in and see what's going on, please say hi. We can go over the schedule. Now, today is Friday, so we're going to be doing new stuff today. We'll be doing new stuff for the next couple days, to be honest with you. It's just the way it is. So we have an assignment that will be up later today that'll be due on Monday, and you can see in the chat there. So we have gotten almost halfway through this unit. So we should be able to finish this unit no problem with the remaining weeks that we have. What's going on, pal? So I got the PowerPoint working and all that stuff, so we will be showing that on your screen as well. I have taken some questions that you would have seen on the PowerPoint in class, and here we are, okay? So that's that. All right, okay. So we did, let's see. Did we do a question like this? We did. We did a percent yield question. So let's do this as a quick review, and we can move on after this question. So quick review. It says, how many milliliters of water are created in the combustion of 15 milliliters of carbon tetrachloride or carbon tetrahydride gas if only blah, blah, blah water were collected? What is the percent yield? I think we did this one exactly, this question exactly. So we're going to start by making the balanced equation. That's always the beginning. Oh, and by the way, I got my windows open. I haven't installed my window AC yet. If I close the windows, it's going to be fairly disgusting in here. So because of that, I got a guy across the street cutting the football field, and you could probably hear the mower. If it gets annoying, mention it. I'll make do. All right, so we have the very first step is to make the balanced equation, okay? And let's see here. So we got combustion of carbon tetrahydride. So CH4 plus O2. That's the combustion. Now, you know the products are always going to be CO2 and H2O because of the nature of this stuff, right? And we have how many milliliters of water are created. So this is what we want to figure out, milliliters of water in the combustion of 15 mils of carbon tetrahydride. If only 0.015 milliliters of water were collected. That sounds like an actual yield. Based on the context of the question, if it was collected or produced, anything like that is another way of saying actual yield. So we want to know what the percent yield is. Okay? So we got to find the theoretical yield first as part of the question, and then we're going to use that to calculate your percent yield. So let's balance this equation so we know what those molar relationships are. Let's see here. I'm going to put a 2 here and a 2 there. That should be good. 4, 4. Yeah, we look okay. All right, next. I got all this. What the hell is going on there? For some reason, my phone that's right up here is doing autofocusing. I got to figure that out, but that'll be a whole nother day. So this is going to be what we start with. Since there's questions over here, this is the only thing that we know for sure. So I'm going to take that information, 15 mils of CH4, and I'm going to slowly convert it to milliliters of water. Now, there's some tricks in this question. If you read the question, it says, how many mils of water are created? Okay, water is going to be a liquid. But then it says carbon tetrahydride gas. So that gives us some freedom for the carbon tetrahydride that we cannot use with the water. Let's get rid of milliliters, and you'll see what I mean in a minute. Go to liters. Now, since it's a gas, I can do the 22.4 liters. Keep in mind, I'm in CH4 this whole time. Okay, I'm labeling it up as I go. This gets me to moles of CH4. Now I can switch compounds and go from 1 mole of CH4 to 2 moles of water. See how I did that? This is the only new conversion factor you've learned. Everything else is review or old stuff. So now I'm in the correct substance. I got to get to the correct unit. Let's get rid of moles. Now, a lot of you guys are going to want to go from moles to liters because that gets you to milliliters. And I understand that, but the problem is this is not a gas. So you cannot use the 22.4. You got to instead go to grams, and water is about 18. But now you have the density, which is 1 grams per milliliter. Do all this math, and you're done. It's not too bad. Okay, so let me bring up the Google, and I'll do a calculator. So 15 divided by 1,000 divided by 22.4. times 2 times 18. And with 2 sig figs, I'm going to get 0.024 milliliters. So this is going to be what we would call the theoretical yield, because in theory, that's the most we can make. We calculated that using the stoichiometry. This is our math. All right? So we discussed the differences between theoretical and actual yesterday. This is our theoretical. Now, with our percent yield question, the last part of it, let me check the chat, see if there's any questions. If you do guys have questions, you got to ask as we go. Doesn't look like any. All right, so we're going to do the theoretical, the actual yield divided by the theoretical times 100. Well, we know both now. The actual yield was given to you in the question. That will always be smaller than your theoretical yield, which is what you calculate. Units are going to cancel out. Milliliters go away. And for the calculator, 0.015 divided by 0.024 times 100. I got 63% with sig figs. That would be your final answer there. Okay, so we did a question just like that, and it's not terribly difficult. And it's just a matter of knowing what you're solving for. All right, let's be honest. It looks crazy. If you didn't know what you were doing and you watched me do this, you would have no idea, and you would be incredibly impressed with my chemical and science skills. But you can now be that person to impress somebody else who doesn't know what they're doing, because you can follow along. You guys with me? Okay? All right, next, we're going to learn some vocab here. Okay? Oh, and now I get the train going. This is not annoying at all. All right, let's talk about these vocab words, okay? Now, in every reaction, I'll give you a moment to look at them while I kind of stall here. You got your limiting reactant and your excess reactant, okay? Every reaction that has 2 reactants, one is going to be called the limiting, one is going to be called the excess. I hate this train. So, with that in mind, you're going to have to figure it out. So, here's the deal. The limiting reactant is the reactant that you will run out of first, okay? And once you run out of one of the reactants, you now are missing one of the ingredients. The reaction stops. So, in other words, the limiting reactant decides how much of the product can be made, okay? Because once you run out of that, you're done. That's it. So another name for this would be limiting reactant or limiting reagent. Both mean the same thing. So don't let that confuse you if you see that If you look it up somewhere or you hear me say reagent by mistake, limiting reactant, limiting reagent, same deal. Okay, your excess reactant is the one where you're going to have a lot left over. It was given to the reaction in excess. So therefore, you're going to have some left over after you run out of your limiting. So you run out of your limiting, the one reactant that's left over was in excess. So that's the excess reactant. The excess reactant, there's so much there, you don't have to worry about it. Now, if you look back at this question, right, the one I haven't erased yet, the CH4 was given 15 milliliters. We didn't mention anything about the oxygen, so we have to assume that this was the excess reactant, and this is the limiting reactant. So CH4 is the limiting, O2 is the excess. In that scenario, each question is going to be different. Part of this math that you got to do is determine which one is which and treat them accordingly. Okay? You guys with me? Where did the 18 come from? This 18. Is that what you're talking about? All right, this 18 is the molar mass of water. Okay? That is the grams per mole. I got that from the periodic table. You with me? Give me some feedback here. You might be the only one here. It might just be me and you again. I know I got one viewer, which is myself, which is almost embarrassing. And then you got your Spider-Man thing going again, right? Okay, give me some feedback here. I'm sitting here hanging out by myself. I'm going to drink some coffee while I wait. Okay, cool. All right, so you got the vocab words down too? Are you comfortable with those? Limiting and excess. We need to be comfortable with those ideas. So let me know your feedback on that, if you got them as well. In the meantime, I'm going to bring up the next question. Percent yield. Okay. All right, good. So in this question, we have, it's worded slightly different, all right? It says when 900.8 milligrams of lead-4 oxide, plumbic, lead-4, whatevs, lead-4 oxide reacts with an excess of carbon monoxide. So right there, it's telling you that the carbon monoxide is the excess, okay? 300.8 milligrams of lead and some carbon dioxide are produced. What is the percent yield? Now, I believe we already did this question, didn't we? If I go back a couple. No, we didn't do this one, but we did one similar. Okay. Let's do this one. All right, just so you could see the words excess and limiting in action and how they apply to this question. So, very first thing you need to do is make that balanced equation. So you got lead-4 oxide. So that's hang on, I lost my screen here. Where are we at? Okay, lead-4 oxide. So you got to do the crisscross and then reduce. And I'm going to react that with excess carbon monoxide. This does sound familiar. I think we may have done this after all. Some lead and carbon dioxide are produced. So lead plus carbon dioxide. Now you got to balance. I'm going to put a 2 here and a 2 there. This definitely sounds familiar. We did this one, didn't we? We may not have done this question, but we saw this reaction. Okay? So, why is it not focusing? All right, so we already did this one. Okay. Now, are you cool with the idea of the carbon monoxide being in excess and the lead-4 oxide is the one that we're going to run out of first? So, oh, hey, Luke. What's up, Matt? What's going on? Good to see you guys. All right, so I know we did this reaction. We may not have done this question, but what I want you to do is tell me, whoever's here, if you're comfortable or not with the idea that the carbon monoxide is excess, and we're going to run out of this first. Once we run out of the lead-4 oxide, the reaction stops, and the only reactant left over is going to be the carbon monoxide because it's in excess. Does that make sense? You guys with me there? All right, I'm going to go to the next question. Okay. Here's the kind of question. Now we're stepping it up a little bit, all right? This is not a hard question. It just demands more work than what we've done before. So it says, what is the limiting reactant in terms of carbon dioxide? So we have to focus on the carbon dioxide product, okay? When 59.6 grams of dicarbon hexahydride, all right, so dicarbon hexahydride. Let me do this here real quick. So dicarbon hexahydride is combusted, and we know one of the products can be CO2 just by the question, but we also know the pattern, so we can kind of predict it right there. Now let's balance this before I address the numbers. I got, I'm going to put a 2 here, put a 4 here, and I'll put a 6 there. That's 8, 14, and now I got a 7. Okay. You can balance that. I just have seen these so many times at Yale. Whatever. Okay. All right. Now, let's address the numbers. It says that we have 59.6 grams of dicarbon hexahydride. So, 59.6 grams. And it's combusted with 2,900 milliliters of O2. It says, what is the limiting reactant in terms of carbon dioxide? So when you see that, what you got to focus on is this guy, 59.6 grams of this, is only going to be able to make a certain amount of that. And the question's asking about CO2. So that's what we're going to focus on. The oxygen is only going to be able to make so much of that as well. But the question is, which one are we going to run out of first? Which one of these reactants? So in other words, which one is going to make the least amount of that? So let's do some math here, all right? When you're presented with a question like this, you have to do work for both of them for it to make sense. So I'm going to do some math here for C2H6, and then down here I'll do some more math for the O2. Now, they're in different units, different amounts, but we want to get to the same thing. So notice it doesn't even mention what units we're curious about. So I'm just going to go to the very first unit I get to, which would be moles. So if I can get both of them to moles of CO2, then I can compare the answers, and you're going to make a judgment call. That judgment call shows that you know what you're doing. That's the tricky part here. So let's get both of these to moles of CO2. And we'll do whatever steps we need to, and then we'll go from there. So I got 59.6 grams. Let's get rid of grams and go to moles. All right, so C2H6, that should be about 30, okay? Each carbon is 12, so you got 24 right there. Each hydrogen is 1, so it's 6. 6 plus 24 is 30. I'm rounding. You won't be. Now, I'm in moles of C2H6, so I could do 2 moles of that. And then it gets me to 4 moles of CO2. So I got this guy cutting the grass and the train going on at the same time, and I can't even turn on a fan because I bought a house without central air. My rant's over. I'm just trying to teach. All right, next. Let's do the math here, okay? So this is about 60. I'm just going to kind of round it to get a prediction here. 60 divided by 30 is about 2, right? And then 2 times 4 divided by 2 is 4-ish. So I'm expecting around 4, okay? Let's get some math going here. 59.6 divided by 30 times 4 divided by 2. Did I say 4? I meant 40. Did I do that right? I did that wrong. I was right the first time. All right, 3 sig figs. I got 3.97 moles of CO2. Now I got to do the same thing and get to the same end point here for the O2. All right? But I got 2,900 milliliters. Now, oxygen is a gas, so I can use that liter thing. 22.4 liters to moles. And the last step would be 7 moles of O2 gets me to 4 moles of CO2. All right? So this gets me to about 312, I'm not even trying that one. I'm too distracted by all the heavy machinery going on outside. Here comes the train any second. Get ready for it. There it is. Stupid train. All right, 2 sig figs. I got 0.074 moles of CO2. All right, so let's look at this one, okay? I don't know if I scared you guys, but no one's saying anything after my little rant there. You might not even be able to hear me. Oh, my God. All right, focus. So, looking at this balanced equation with all the information given to us, I did some work here, and it got me to this point. So let's determine and make a judgment call as to what this work actually means for us. The amount of C2H6 that we have to start is capable of producing this much CO2, almost 4 moles. Okay? The amount of O2 that we had to start that was allowed to be used in this reaction is capable of making 0.074 moles. Way, way less than 1. Way, way less than half. Less than a tenth. Okay? So, if this guy is only able to make this much, once this much is made, we now no longer have this O2. That O2 runs out after this much of CO2 is made. Keep in mind, O2 is a reactant, CO2 is a product. We're trying to link those two together with the amounts that we have and determine, in theory, how much we could make. Now, that's a key word. In theory. So here we go. We got to make a decision between this number and this number, both of CO2. We're going to determine that the lower amount is the theoretical yield. Listen to this phrasing. The smaller amount is the most you can make. The smaller amount is the maximum possible. In other words, the theoretical. So all this work that we did gives us 3 pieces of information. He doesn't even care. He's on his big, expensive mower smoking a cigarette. He's cutting a football field. He's not even doing a good job. Anyway, I guess I'm jealous. He's got a big mower. All right, so this is going to be called our theoretical yield. Your theoretical yield is for your product. Your limiting reactant is what decides the theoretical yield. Remember that? This is your limiting reactant, oxygen. Don't get these mixed up because people do it all the time. They call this your limiting reactant. Once you know what this is, the theoretical yield, that is linked to your limiting reactant. This is a product. How could you call that your limiting reactant? Get it? So if that's your limiting reactant, you have no choice but to call that your excess reactant. Done. There you go. You figured out those 3 pieces of information from doing those 2 steps. Thanks, Luke, for calming me down. I lost it there for a minute. I appreciate that. Okay. That's a reasonable question, I think, right? Not too bad. Now, for this question, it's real similar, but this one's asking what the excess reactant is. Now, based on everything we just did, you got to do the same work. You got to do all the same stuff in order to find any of the 3, theoretical, excess, and limiting. But you find all 3 of them at the same time. So you might as well start getting into the habit of labeling those 3 no matter what's happening. Okay? So if you're given a question where it says, find a limiting, find the excess, find a theoretical yield, whatever, it's the same work for any of those 3 scenarios. So let's do that for this one. What is the excess reactant in terms of the precipitate? All right, so you need your solubility rules. In the reaction of lead 4 nitrate, and sodium chloride. All right, that's all it's giving you. Okay, you got to figure out the rest. Well, it's a double. I know that for a couple reasons. It gave the word precipitate as a clue, and also it's 2 ionic compounds. So I'm going to get sodium nitrate as my 1, and then I'm going to get lead 4 chloride as the other. Let's do it this way. Run out of room here. Here we go. Okay. All right, now we got a balance. I'm going to put a 4 here and a 4 there. Okay? All right. Now, let's see what numbers we got. It says the reaction of 1.46 grams of lead 4. Lead 4 nitrate. And 24.9 grams of sodium chloride. Now, some of you are thinking, maybe, maybe not, but I get this question every semester. Wouldn't this automatically be the limiting reactant because it's a smaller amount? Maybe. You don't know that yet because you haven't done the math to figure out what the theoretical yield is. The fact is that these 2 compounds, even though you have way more of this possible, way more of this available for the reaction, they have different molar masses. So the fact that their molar masses are going to be very different, that's going to possibly change that assumption. So you got a 50-50 chance of saying it's this one, okay? But there's only one way to really know for sure. Now, we're interested in the precipitate, so that's going to be the lead 4 chloride based on the solubility rules. I'm going to switch markers here. This red's starting to act up. Let's do green, okay? All right, so we're going to have to do work for each. Keep in mind that the question's simply asking which one is the excess reactant. And it's just asking you to identify which one that is. All right, so I'm going to do some work for the lead 4 nitrate, which is 1.46 grams. And I got to do some more work for the sodium chloride, which is 24.9 grams. All right, here we go. We're going to convert each to moles. We're going to use the molar mass. Now I'm just going to look the molar mass up for that lead 4 nitrate because it is what it is. Now there are websites where you can just find a calculator for a molar mass, and you put in the formula or the name, and it just gives you the molar mass. That's what I've been using for a long time now, and it's been working out pretty well. So for the lead 4, I got 455.2196. I'm just going to leave it at 455 for ease. Now I'm in moles. Let's get rid of moles of lead 4 nitrate, and I want to go to moles of lead 4 chloride. Just happens to be 1 and 1. Okay? Do the math, you get your number. If the question was any more specific, I might have to carry this out to get to a certain unit, but I don't have to do that in this case. You'll see questions like that eventually. Okay. All right, next, let's get rid of grams of sodium chloride and go to moles. I think that's 58 off the top of my head. Pretty sure about that. And we got 4 moles of sodium chloride, and we're going to 1 mole of lead 4 chloride. Notice as we get further and further along, we do this more and more. I'm not labeling as much because I'm trusting that you guys are following. And this step here where you go from moles to moles, you're switching chemicals. All right, so you're just switching from one substance to another. Now, let's do the math here. So 1.46 divided by 455. I got point with 3 sig figs, 0, 0, 3, 2, 1 moles. And then for this other one, this other math, 24.9 divided by 58 divided by 4. I get 0.107 moles. All right, now we got to make that judgment call. We got to compare the two answers, and you got to find the smaller number. That smaller number is always going to be your theoretical yield. Your theoretical yield is always linked to your limiting reactant. That means the other one is your excess reactant. Hopefully you see the logic there, okay? And it's not too bad. All right. You guys got any questions? I think the train left the station, and the mower guy is now in another part of the field. Anyway, you guys okay with everything we just did? I'm going to put up an assignment shortly regarding a similar problem where you have to find either the excess limiting or theoretical. You don't need many questions. I might give you one, maybe two, all right, just so you can have that done by Monday. Now, these random assignments throughout the unit are only going to be worth participation. So if you do them and turn it in on time, full credit. But then the last assignment for the unit is going to be worth like a quiz grade where I check it for accuracy. So any questions at all? Matt's giving me a thumbs up. I'm hoping everybody else is still here. Pal and Luke, you guys good? Luke, did you switch devices or an account somewhere along the way? Looks like I got it says Luke A, and then it gives your full name and another time with a different picture. Whatever, it doesn't matter. I know who you are. Good enough. So everybody's saying we're good. Pal might have left early. All right, Pal's still here. All right, cool. You guys are all checking out as being good. I'm going to now spend some time making this assignment. I got to do one for the other class as well. So I should have them up by like 10:30, okay? And you'll have all weekend to do it. Monday at noon is when it'll be due. And at that point, before that's due, we'll have another opportunity to ask questions, okay? No, it's not too bad, dude. If you go back and you watch... Now, I'm not sure what you mean. You haven't been on the stream for a while. But if that means you haven't watched the videos, just go back and watch the videos. No big deal. They're like a half hour, some are even 15 minutes or so. It's not that bad. Breeze through them, get caught up, and you'll be good. All right? This is not bad. It does lean a lot on previous units, though. So there's that. All right, guys. I'm going to take off. I'm going to get that assignment figured out, and I will see you again Monday. I'll do 8 and 9. Don't be surprised if that changes based on weather, like we've talked about, but expect 8 and 9. All right? And then Monday we'll do more questions, and we'll keep pushing it and do more and more because there's a good amount more that we got to do. Okay? Cool. Have a good weekend, guys. I'll talk to you Monday morning.